In this video, we'll be simulating the properties and characteristic of a balanced Y-connected load. So for experiment 1 of electrical circuits 2 laboratory, so we have the following objectives. So to measure the phase and line voltages of a balanced Y-connected load, and then secondly to measure the phase and the line current of a balanced Y-connected load. The learning outcomes for the laboratory are to verify the relationship between the phase and the line current of the given balanced Y-connected load. So to verify the relationship between the phase and the line voltage of a Y-connected load. And lastly, to verify and calculate into the power factor of the balanced three-phase load. So to simulate the properties, characteristics of the given load, okay, so we'll be using the multi-sim software to simulate. Okay, so this is the circuit. Okay, so that we need to have in order for experiment number 1. Okay, I mean in order for the simulation. Okay, so in experiment number 1 to be performed, okay, so we need to build this circuit, and then we follow, okay, so the procedures, okay, and for the results, so we have these tables. Okay, so the line and phase voltage. Okay, so for table 1.1, table 1.2 is for the current and the power factor. And then for table 1.3, so this is for the phase difference, okay, so of the or the phase angle between the line voltage and the phase voltage. Okay, so for the graph section, okay, so you need to have the or you need to save later on the waveform um, generated by the oscilloscope, and then of course the observations and interpretation of the data, and then your conclusion. Okay, so this should be the content of experiment number 1 for EE282 uh, electrical circuits 2 laboratory. Okay, so what we need to do is to uh, open. Okay, so what we need to do is to first is to run the multi-sim software. Okay, so if you have already installed it, so you can, okay, so you can run the software. Okay, so you can see the evaluation period is or will be expiring in 6 days, but you can extend the status. Okay, so you may need to create an account. Okay, so in uh, National Instrument, okay, website, you can create your account so that you can extend the evaluation period of the free trial. of the software. Okay, so just click evaluate, and then for the meantime, okay, so you can click no, and then you will be directed, no, so you'll be, or a new window will open. Okay, so this is where we simulate, no, so the circuit, so as shown in the laboratory experiment, as given in laboratory experiment number 1. Okay, so first is we need to have the source. Okay, so you can click this button here. Okay, so place source, and then you can click power sources, this one, and you can click three phase Y. Okay, and then click OK, and then you will be okay, so you'll be given with a Y connected generator. You can place it anywhere, not so in the working station or working area. So after which you click this one, you close the window. So as you can see by default, so you are given with a Y connected generator. So the frequency is 60 hertz. The voltage, okay, so to know more about the properties of the generator, so you just click it here, double click, and then you will have the um, line to neutral. Okay, so the 120 volts given in the generator is the phase voltage, no? So 120 volts, so let's leave it as 120 volts. Okay, so you may click it. Okay, so the frequency is 60. You can alter this one. You can also alter the phase voltage. Okay, so but for the entire course, so of the experiment or entire course, no, in experiment 1, so we just leave it as 120 and 60 hertz. Okay, so click OK, and then you can zoom in or zoom out the working area. So you can use the scroll button in your mouse. Okay, or you can click. Okay, so the zoom in and zoom out button here. Okay, so now after having the three-phase source, so we need to connect, no? So we need to connect the other end or the neutral. Okay, so the neutral line of the generator to ground. Okay, so just click again the sources, and then power sources, and then ground. Then click OK, and then put the okay ground. Okay, then connect it. Okay, so to connect the generator to the ground, just click the neutral line of the generator, and then connect it to the ground. Okay, so the software will automatically connect one component, okay, so to the other. Okay, so you can adjust this one like this, okay, or go it like this one. Okay, so we have now the three-phase source. Okay, so this is line 1, line 2, and of course line 3. Okay, so for the balanced Y connected load, so we can click the place basic button, this one. Okay, so and then okay, so you can go downward. Okay, so click Z load, this one. Okay, and then you can have the Y connected load. Okay, so this one Z load 1Y. Okay, click OK, and then you will be given automatically with the balanced Y connected load. So which is is okay. So this is for this load. Okay, so the balanced Y connected load. Okay, so is composed of three elements. No, so we have the resistor in series with the inductor and is connected in parallel with the capacitor. No, so to which the values are given as, so 1 kilo ohms for the resistor, 1 millihenry, 1 microfarad for the capacitor. Okay, so you can alter, no, so you can alter the values, no, so of the resistance, inductance, and capacitance. Okay, so uh, okay, so just have the other, okay, buttons or tabs, no, so remain as is, and also the value, no. So we'll use the default values, no, so provided in the software. That is for the resistance, that's 1 kilo ohms, inductance, that's 1 millihenry, and for the capacitance, that's 1 microfarad. Okay, so and then uh, okay, so the neutral point of the load is also required to be connected to the ground. Okay, so you can click again, no? So the play source, and then click ground, and then click OK, and then okay, you may put it here. Okay, so then click close, and then connect. Okay, so you have now the three. Okay, so the three phase load. Okay, so with the neutral point connected to the ground. Okay, so we just need to connect, no, so the lines to the load terminals. Okay, so this one for line 1, so this will be connected to uh, this terminal. Okay, so line 2 will be connected to this terminal, and then of course line 3 will be connected to the other load terminal. Okay, so you can adjust the connector, so you can place it there, and then also the other end. Okay, so in this um, portion. Okay, so we have now the generator and the uh, balance Y connected load. Okay, so to run, so you can click this button or just press F5. Okay, so in your keyboard. Okay, so according to the procedure, okay, so after building the circuit, no, so in figure 1.1, so we need to measure the line voltage and the phase voltage. Okay, so using a voltmeter, and then record the results, no, so in table 1.1. Okay, so okay, so we can, okay, so perhaps we can have, okay, so we can delete this one, and okay. Okay, so in table 1.1, so we are being asked not to obtain the line voltage and the phase voltage. Okay, so using a voltmeter. Okay, so to find the voltmeter, so you can have it uh, in this side. So click multimeter, this one. Okay, so and then put it here, and then you can double click, and then click it, set it as voltmeter in AC setting. Okay, and then click close. Okay, so to measure the line voltage, no, so Okay, so to measure the line voltage at the load terminals, so we need to connect one end of the voltmeter, okay, so to one terminal of the load, and then of course the other end to the other load terminal. Okay, so just like this one. So we have now the um, okay. So we can okay. Okay. So this measures the line voltage, no, so of the at the load terminals, and then we also have the phase voltage, no. So we need to have another voltmeter. Okay, so you can place it here, and then so this voltmeter will measure the. So again, do not forget to set it to AC. Okay, so you can, by the way, set the meter to ammeter, voltmeter, ohmmeter, or it can measure the noise in decibel. Okay, so for this experiment, we'll be using it as an AC voltmeter. So just set it to, okay, so voltmeter and then AC. Okay, so this one. And then click close. So connect the, or to measure the phase voltage. So we need to connect one terminal of the meter to line 1, and then of course the other end to the neutral point. Okay, so the wattmeter 1, I mean the voltmeter 1 will measure the line voltage, and then the um, voltmeter 2 will measure the phase voltage. Okay, so of the load, I mean at the load side. Okay, so to enable the circuit to run, so you can run this button here, click, no, and then so the circuit is already running, and then so you can double click, no, so you can double click the meter. So the, so as you can see, the line voltage is 207.861, and then the um, phase voltage, no, so as you can see, that's 120.008 volts. Okay, so you can record these values uh, to the table, okay, and then proceed to the next, okay, so activities, I mean procedure, no. So you can close this one and then stop the simulation. And okay, so for the next procedure, so we use, no, so an ammeter to measure the current drawn by the three-phase load. Okay, so and then uh, we record, no, so the result in table 1.2. Okay, so we can remove the voltmeter first. Okay, so and then set aside, no, so the meter, and then this one will also be removed. Okay, so now this time we use the meter one as an ammeter. Okay, so you can click it here, A, set it as ammeter, and then do not forget to, of course, set it into AC. So the straight line represents direct current. Okay, so for the ammeter, so you need to insert, no, so the ammeter, so in between the uh, source and the load. Okay, so you can remove this one, and then we can insert, no, so the ammeter. Okay, and then connect the ammeter to the Now, one end of the ammeter to the source and then one end of the ammeter to the load terminals. Okay, so right after which we can run the simulation, and then as you can see the current, no, so the current drawn by the load is 128.288 milliampere. It's obviously the current from the source, no, so the line current from the source is the same as with the current flowing per phase, no, so of the three-phase load. Okay, so whatever current uh, flowing, no, so at the uh, or current flowing from the generator terminals will be the same, no, so as with the current absorbed per phase by the load. Okay, so that is for a Y connected load. Okay, so the line current and the phase current, no, so are equal or the same. Okay, so this would be for the current. Okay, so next is to okay, so the next one is to measure the power factor of the circuit. Okay, so we use the wattmeter. Okay, so the wattmeter in the multi-sim can measure the power factor, no, of the given circuit. Okay, of the three-phase load. So in using the wattmeter, so to measure the power factor, so the wattmeter must be connected, no, so to the following points, no, so the potential coil must be connected to line and neutral, whereas the current coil will be inserted to uh, one of the line, no, so of course the line here, okay, so this one, so is the same line as to where the potential coil is being connected. Okay, so the next step is to measure, no, so we can remove the ammeter. Okay, so we can stop the simulation first before you can edit, no, so the circuit. So you can click this red button here to stop the simulation, and then perhaps we can remove the what no, the ammeter. Okay, so connect it there, and then okay, so we can delete this one, and then for the wattmeter, so at this side you can have the wattmeter. Okay, so the wattmeter is composed of two, no, so elements, uh, the ammeter and the voltmeter. Okay, so the current coil, okay, so this terminals here, okay, so will be inserted to, okay, so let's take a look at first the potential coil. So for the potential coil, as per with the problem, I mean the solution, no, the procedure, so it will be connected to the one of the line or line 1, and then the other end to the neutral point. Okay, so you have now the uh, potential coil. Okay, so the current coil, this one, will be inserted to one of the line. Okay, and then that line must be the same line as to where you connect the um, potential coil. So since one end of the potential coil is connected to line 1, then therefore the ammeter needs to be inserted. Okay, so this will be inserted to line 1. So we can remove this one. Okay, and then uh, we can connect the positive terminal to the source, this one. Okay, And then this one will be connected to, okay, so we have now the, okay, so we have now the current coil inserted in line 1. Okay, so as you can see, and then the potential coil connected across line 1 and the neutral. Okay, so to measure the power factor of the circuit, so we need to, okay, so run the simulation, and we can double click the wattmeter. Okay, so as you can see the wattmeter, no? So the wattmeter provides 14.402 watts. So just never mind the power as of now. So basically that is the power drawn per phase of the load. But what we are up to is the power factor of the circuit. Okay, so the power factor of the circuit is 0.93546. Okay, so you record, okay, so this power factor, no, so in table 1.2, and uh, okay, we proceed to the next procedure, that is to evaluate, no, so the phase difference of the line and phase voltage. Okay, so we can stop the simulation, and okay, so in the next procedure, so we need to use an oscilloscope, okay, so to identify the phase difference between the line voltage and the phase voltage, no, so of the Y connected load. So with the same circuit, okay, so we remove the wattmeter, then we connect the, okay, so the load, okay, so to the source. So the oscilloscope can be found, okay, so below the wattmeter, okay, so in this side. So as you can see, so we have there, okay. So take note that the oscilloscope will uh, plot, no, so the voltage waveform, not the current waveform, no. So now we need to evaluate the, okay, so um, or we need to display, no, so the waveform of the line voltage. Okay, so therefore the channel A, okay, so of the oscilloscope will be connected to the lines 1 and 2, no. Okay, so as you can see the oscilloscope, so you can change the color if you want. Okay, so perhaps you can click blue, or uh, okay, or you may use the first color red if you want. Okay, so the channel 1 of oscilloscope will display the waveform, no, of the um, line voltage, whereas channel 2 will be used to display the waveform of the phase voltage, no? So we connect, okay, so the positive terminal of channel B to line 1. Okay, so perhaps we can, okay, channel 2, and then of course the, okay, so negative of channel B connected to the neutral point. Okay, so in this way the oscilloscope will display, no, so the line voltage. Okay, so in channel A, and then in channel B, so that is the phase voltage, no, so of the uh, Y connected load, balanced Y connected load. So to enable the oscilloscope, so we need to click this one run button and then double click the oscilloscope. Okay, so as you can see in the procedure, so we are asked to set, no, so the channel 1 and channel 2 to 100 volts per division, and then, okay, so we change this to 100 volts. Okay, so 100. Okay, and then for channel B, so the same thing, so that's 100. Okay, so 100 volts. So as you can see, the waveform also is moving. So because this is a real-time display, so that means uh, the moment you switch on the source, so the oscilloscope displays the waveform at with respect, no, so to the present time. So you can see the time is moving. Okay, so that means at this particular point the voltage is this one, and then the voltage also the channel 2 is this one. Okay, so we scale the time per division into 5. Okay, so as given in the uh, procedure. So to enable the oscilloscope to, okay, so to enable it to, okay, so you can set it to single. Click this one. Okay, so and then you will see the steady form of the wave, no? So uh, to identify which one is, okay, so to identify which one is, by the way, you need to click this, no? So AC. Okay, so to identify which one is for channel A, so you can choose to display only channel A. Okay, so by clicking 0, so as you can see the this waveform is for channel A, and then of course the smaller one is for channel B. Okay, so okay. Now as you can see, we need to identify in order for us to identify the phase difference. No? So by the way, you can save this one, like, okay, so this one, click save button, and then you may Okay, so you can perhaps take no, sa screenshot. Okay, so of this portion here. Okay, so this will be, or you will be pasting it in the graph later on. Okay. Okay, so click single and then okay. So in table 1.3, so we have here the number of divisions. Okay, so this represents the number of divisions that separates no, so the waveform, the two waveforms. No, so if you try to look at it, okay, so uh, we have this one as okay, so this would be one division. Okay, so the bigger uh, divisions will be okay, so this would be one division, two. Okay, so let's say with respect to this point, okay, reference point, so this would be one division, two divisions, three divisions, four, and so on. And if you try to look at per division, there are subdivisions. Okay, so these subdivisions in a given big division is okay. So there are one, two, three, four, five. Okay, so meaning to say this single subdivision in the bigger division will be scaled as 0.2 division, no? So 0.2, 0.4, 0.6, 0.8, then 1. Okay? So as you can see, uh, the okay, the number of divisions with respect to okay, so or the number of divisions that separates no the okay, so the um, phase voltage waveform and the line voltage waveform can be okay, so evaluated. Okay, so if we try, for example, if we try to look at it in this portion here, okay, so with respect to this point, okay, so the number of divisions that separates between the two, no, so the two waveform would be okay, so this would be point 0.2. Okay, so point 0.2, and you have there another point 0.2, but then since the okay, since the bigger waveform is in between okay, so that's in between the subdivision, so that means we can approximate so the difference between the two as okay, so you better take a screenshot no, so of this one. Okay, so for you to be able to zoom it. Okay, so as you can see, we may say that the difference between the two is around zero point 0.3. No, so with respect to this one, so that's zero point 0.3 division. Okay, so that's 0.3. So you record it here. For example, that's 0.3 division. And then the degree per division, this can be calculated. Okay, so by having 100. Okay, so that's the degree per division can be calculated by dividing 180 by the number of divisions in a cycle. Okay, so as you can see, uh, if we try to, okay, okay, so if we try to look at, okay, starting from this point, say the bigger sine wave, okay, so you may say that the total divisions covered in a single cycle is given by that's 1, 2, 3. That's around 3.3. No? So this is point 2, and then it does not reach point 4 subdivision. So we can say that the total number of divisions, no? So in a cycle is 3.3. No? So this would be 1 division, 2, 3, and then the okay, the one cycle ends here, so that would be uh, 3.3, no? So divisions. So we may say that the total number of divisions, no? So okay, so that would be 180 divided by 3.3. Okay. So the phase difference then is the product of the number of divisions, that is zero point 0.3 divided by or multiplied by 180 divided by 3.3. Okay.